Hello and welcome. So in this video, we are going to be looking at chapter 5 of physics, right, of Eric Mazur. Okay, and this chapter is all about energy. So I assume that you've already done chapter 1, 2, 3, 4. So you've looked at velocity, acceleration, you've looked at momentum as well. So energy is just the natural progression in that chain of physical properties that we are learning about, right? Okay, so we're going to go on to energy, and chapter 5 is closely linked to chapter 7. So right after chapter 5, we're going to go to chapter 7, which is like a continuation of chapter 5 almost, right? Okay, so we have something called kinetic energy, okay? And it is really important. It is the energy that is associated with the motion of an object, right? So if an object is moving, it has some form of kinetic energy, okay? And also important is that it is a scalar quantity, right? So it has no direction, it is just a value, just a magnitude, right? So this is what kinetic energy is, and the formula for it is given by this 1/2 mv squared, right? So it depends only on the mass of the object and the speed at which it is moving at, or the velocity, okay? But it doesn't matter if the velocity is positive or negative because we square it, right? So something moving in one direction at a velocity of 10 and something moving in another direction at a velocity of -10. Given that they have the same mass, then they would have the same kinetic energy because we're squaring it, right? Okay. And the SI unit of kinetic energy is the joule, okay? 1 joule, which a joule is just a kilogram meter squared per second squared, but we just use joules, okay? And kinetic energy is one of the most important forms of energy that you're going to encounter, and it is going to keep coming up and coming up. So make sure like you understand what it fundamentally means. It is very similar to momentum in the way it works, right? Because momentum is mv, but kinetic energy is half mv squared. So they both depend on the same variables, just in different ways, right? Okay, then we have something called relative velocity. Now, uh, this is basically understanding that velocity actually depends on how you are looking at it, right? It depends on perspective. So basically what this means is if, so let's just say I have a car, okay? I have a car that is moving in this direction. Let's say it is moving at 20 meters per second, for argument's sake. And then I have a person standing here, is just standing. He's not in front of the car, don't worry. He's on the side of the road, so he's not about to get hit by the car. And he has 0 meters per second, okay? And then let's say there's a cyclist. Okay. We have a cyclist, and the cyclist is moving at 5 meters per second, okay? So now, we as the observers of this, we are in the perspective of this guy, right? So we are moving at 0 meters per second. So from our perspective, this car is moving at 20 meters per second. This bicycle is moving at 5 meters per second. But now we have to ask ourselves, what if you were the cyclist, right? If you're the cyclist, you are moving at 5 meters per second, and this guy is moving at 20 meters per second. But because you are moving while this guy is also moving, from your perspective, you are going to be not moving at all, right? So if you are moving to yourself, it is almost like, okay, it is not almost, it is like you are not moving at all, but everything else is moving, right? So from the perspective of the biker, is not moving from his own eyes, right? And this car is going to be moving only at 15 meters per second because of that extra 5 meters per second that this guy has, right? And this one that was 0 for us to the biker is actually going to be 5 meters per second towards him, right? I hope you can see that distinction. Okay, let's try for the car. To the car itself sees itself as stationary, right? But then it is going to see this guy as moving towards it at 20 meters per second because it is moving towards the guy at 20 meters per second. And it is moving forward at 20 meters per second. The biker is moving towards it at 5 meters per second. But because it is faster than the biker, right, it is going to see the biker as moving backwards at 15 meters per second because from the perspective of the car, the biker is actually moving backwards because the car is faster. Okay, I hope you can see this. So fundamentally, what this idea means is that actually, for each one of us, we are all stationary and everything else is moving, right? So if you're in a car and you're sitting, from your perspective, the car is actually stationary and you're just watching a slideshow. So the trees are moving, the buildings are moving, the road is moving, but the car is stationary. So this is the fundamental idea of relative velocity, right? And the formula is given by this, right? The relative velocity of object 2 relative to object 1 is given by this v12, and it is v2 minus v1. So just make sure you don't mess this up because in this case, our perspective is the perspective of object 1, right? And object 2 is what object 1 is observing. So I hope that makes sense, right? So the relative velocity v12 is the velocity of object 2 relative to object 1, right? And v21 will be the velocity of object 1 relative to object 2, right? And you can see that the formula just swaps around logically, right? Which means v21 is actually going to be negative v12, right? Which makes sense from this because to the biker, it is 15 meters to the right, but to the car, it is 15 meters to the left. So they are the same value, but just different directions, right? Similar situation between the guy and the car. 20 to the right, 20 to the left. Same value, opposite directions, right? Same between the biker, 5 to the right, and the guy, 5 to the left, right? I hope that this makes sense. It is absolutely important. So just don't mess up the order, right? Okay, but now relative speed, again, we already know from previous chapters, speed is just the magnitude of velocity. So it is easy to see that the relative speed is just the absolute value of the relative velocity, right? Which means the relative speed, v12, would be equal to v21, right? And this is for speed because we only care about magnitude for speed. We don't care about direction. Okay, and then some theory we can look at is this. In a collision between two objects, the velocity of one relative to the other is relative velocity, okay? And the magnitude is relative speed. So we've already discussed this, right? And then there's something called the state of an object, which is just the condition, okay? As specified by some complete set of physical parameters. So state, just think of it as what physical parameters can I use to completely define this system or this object, right? And usually we use energy. So energy that is associated with the state but not the motion is called internal energy, right? But don't worry too much about it. It isn't as important, okay? We can also consider a system of two colliding objects to be isolated during a collision such that momentum stays constant, okay, for all the collisions we study. So again, this is building up from chapter 4, right? We already know what the isolated system is. So in this case, we consider colliding objects to be isolated systems unless specified otherwise. So if a question just says collision, you take it to be isolated, even if they don't specify that it is isolated. The only time you don't take it to be isolated is when they don't specify. Sorry, when they specify that it is not isolated. But if they don't specify, then it is always isolated. Okay? So again, momentum remains conserved during a collision. This again is an idea that we are familiar with. Okay, so that's relative velocity. We can now go into the nitty-gritty of collisions, right? And when objects collide, we can define the characteristic of that collision by something called a coefficient of restitution, right? And the coefficient of restitution is a positive unitless quantity that tells us how much of the initial relative speed is restored after the collision, right? So how much speed remains, how much speed is not dissipated, right? And the formula for this, for coefficient of restitution is just the final relative velocity divided by the initial relative velocity, right? Okay. But now, if we go to the formula, V1 choose V2 minus V1. Okay, so that is exactly what they have, right? Okay. Okay, there's always supposed to be a negative. So use this formula instead because it does have the negative. Okay, so this is our formula for coefficient of restitution. Okay. I'm just struggling to see why we have not included a negative here, but uh I am sure of like the formula as it is, this one. So just use that one. Uh yeah, with this, I'm sure the negative is inside the formula because it will be V2 minus V1 and V1 and V2 minus V1. Okay, but this is the formula we use for coefficient of restitution. And remember, what it physically means is how much of the initial speed is stored after a collision. So if your coefficient of restitution is 0.5, it means now your entire system, the relative speed is now half the amount it was before the collision. So some energy dissipation must have occurred. Okay, so now using the coefficient of restitution, we can classify basically what type of collision we have, right? And the three types we have, or the four types we have rather, are elastic, inelastic, totally inelastic, and explosive, right? So the most common one we deal with, which is actually impossible in real life. So this is impossible in real life. It is an elastic collision, right? But let me say close to impossible because you never know what can be discovered by science later on. But as far as I know, currently, it is impossible to have a completely elastic collision. We can have something close, but never exact. So close to impossible in real life. Okay. And for elastic collision, what it basically means is the velocity after is equal to the velocity before, right? So there's no change in relative velocity, which means your kinetic energy is constant. It doesn't change. So there's no change in kinetic energy. There's no change in velocity of your system, right? And this is relative velocity, not just a single velocity, which means your coefficient of restitution is 1. So what that means is that it is saying after the collision, everything is going to go back to basically exactly how it was before the collision, right? And this is what we treat a lot in theory. We assume elastic collisions a lot, but it doesn't actually happen in real life, right? And when you have an elastic collision, it is going to be classified as reversible, right? So an elastic collision is reversible and the kinetic energy is constant, right? Okay, I hope that makes sense. Now, what you must also understand is the individual, right? The individual velocities can still change, but the relative velocity is going to stay constant. So, for example, maybe if I have V1 and V2, my V1 initial can be maybe 2, my V2 initial is 7, right? Which means my V12 initial is 7 minus 2, which is 5. After the collision, V12 final is going to remain at 5, right? Actually, so it is going to remain at 5. Let's just assume we are dealing with the speeds, right? Not the velocities. Okay. So let's assume we're dealing with the speed. Then now it is very possible that now V1I becomes negative 2 and V2I becomes what? 3. So then it becomes 3 minus negative 2, which is still 5, right? So the individual velocities can change, but the final, sorry, this should be final. The individual velocity can change, but the relative velocity is going to stay the same before and after the collision, right? So the relative speed. Okay. So if we go back to here where I was puzzled about it, the reason is because this looks at speed. So the speed stays the same. But when you look at it in terms of velocity, you have to add that negative there, right? Okay, so that is an elastic collision. So if we're looking at this as velocity, this should be negative 5, right? But we're looking at it as speed. Because what actually happens in an elastic collision is the velocity is reversed after a collision. Okay, but it is the same in magnitude. Then we have an inelastic collision, and this is what happens in real life, right? So in an inelastic collision, the final relative velocity is less than the initial relative velocity, and the final kinetic energy is less than the initial kinetic energy, right? So this means some energy dissipation has occurred, basically, right? So some energy has been lost, which is why your final kinetic energy is now less than the initial one. So it's pretty straightforward, but we rarely deal with this in theory because it becomes difficult to account for loss of energy, but you can deal with it. And then we have totally inelastic collisions, right? And this is also close to impossible, right? And the reason is because in this type of collision, the final velocity just becomes zero immediately. So what that means is somehow after the collision, they both just stop moving, like they stop completely. And our coefficient of restitution is 0. Now it is very possible to happen. Like if you take maybe a jelly-like substance. So if you take a jelly and you throw it onto the wall, it just splatters on the wall, right? Okay, that's not a good example. Let's say we take a okay, still a jelly, but not a very soft jelly, a jelly that is a bit thicker, and then it just stays on the wall. It sticks to the wall as you throw it. It stops moving. So that is close to totally inelastic, but it won't be zero. It will just be very close to zero 0.000 something, because actually the jelly does move. It is just a very small movement that you can see, right? So it is very impossible for velocity to just become zero. But again, we can treat this in real life, right? So that's a totally inelastic collision, okay? And what you should also know is that, okay, so the kinetic energy in this case also goes to zero, right? Because the velocities go to zero. And then the final thing we have is an explosive separation, right? And this is where your coefficient of restitution is greater than 1, because actually your uh your kinetic energy increased and your final velocity, your final relative velocity was greater than the initial one, right? And this is very possible, but it is almost like the opposite of inelastic, right? Because for you to get an explosive separation, you have to put in some energy, right? So I would say some energy was injected. That's not a good word, but anyways, injected into the system, right? Was transferred into the system. So for me to create an explosive separation, let's think about a bomb, for example. For a bomb to go off, there was chemical energy that needed to be used, right? So it is possible to get an explosive separation. It costs energy, right? So it costs energy for an explosive separation, but for an inelastic collision, you lose energy, right? So they both involve some transfer of energy. So for an explosive, energy goes into the system, right? But for an inelastic, energy goes out of the system. For an elastic, energy does not go in or out, right? And for a totally inelastic, all energy leaves the system, all energy. So actually, let me just say some energy for inelastic, but for total inelastic, it is all energy. Okay, I hope you can see what is going on here, right? And then for an elastic, the system just stays as the system. Nothing changes, right? Okay. So that is it for the types of collisions. It might seem like a lot now. Don't stress. When you do questions, you're going to see it is not actually that bad. You just need to know the like you need to know this for each case. So you need to know, okay, elastic E is 1, inelastic E is between 1 and 0, totally inelastic E is 0, explosive E is greater than 1. So if you can understand how E changes and what E means, then you will be fine, right? Okay. Uh, okay, so that is for collisions. Then we can now look at actual conservation of energy, which is actually the topic of this chapter. Okay, but you can see it is very, very brief, right? So I honestly don't know why this chapter is called energy, but in chapter 7, we go even deeper into energy. So don't stress at all. We are still fine, right? So the energy of any system, okay, is the sum of kinetic energies and internal energies of all the objects that make up the system, right? Okay, so that seems like a lot, but we already looked at kinetic energy, right? We looked at kinetic energy, and what we're now saying is total energy is kinetic energy plus something else called internal energy, right? And uh, the way I think about it when I think of internal energy, to me, internal energy is just physicists trying to avoid responsibility, right? because, and you see in chapter 7, there are lots of different types of energy that we can have, like a lot. So what we do is we just, in this course, for example, we only deal with a few of them. So we deal with kinetic, we deal with potential, and yeah, that's all we deal with. And there's a bunch of other energies. So what we do is we don't know what these energies are, so we just lump them up together. So there's chemical, there's nuclear, there's solar. We lump them up together and call it internal energy so that we don't have to account for them, right? So it is very lazy, but it works, right? Because actually you can say energy is actually kinetic plus chemical plus potential plus what else is there? Electromagnetic plus nuclear plus solar, and you can keep going on and on and on and on because we know. Okay, let me leave this in actually. Hey, yo, what just happened? Sorry. Uh, because we know from the law of conservation of energy that, where's my page? That energy can be transferred from one object to another or converted from one form to another, but it cannot be destroyed or created. So what I want to emphasize here is one form to another. There are many different forms of energy, and even more keep getting discovered, right? But we can call all of these energies just internal energy of the system, right? And just say, okay, we have kinetic plus everything else, but everything else is actually just internal, right? I hope that makes sense. So the energy of a system, and this is the total energy, right, is given by kinetic plus internal, right? And the law of conservation of energy requires the energy of a closed system to be constant, right? So the change in energy is zero, final energy is equal to initial energy. But now we only have a formula for kinetic energy, right? We don't have a formula for internal energy. So if we want to do calculations, we can say, okay, K plus E int initial is equal to K plus E int final. But now we don't know how to quantify that. We only have formulas for K. So the question could be, how do we deal with this formula? And the answer is we don't really deal with it. It is pretty useless in the grand scheme of things because in chapter 7, we look at a way of classifying energy that makes it much more easy to kind of, where's the word? Kind of analyze, and that's mechanical energy. But we're going to get to it, so don't stress. But for now, we just need to know that energy, total energy, is just kinetic plus internal, total energy. Okay. And finally, we can look at a closed system. And a closed system is one in which no energy is transferred in or out. So the energy of a closed system remains constant, right? And now, just make sure you understand. And let me just move this down. Make sure you understand that a closed system and an isolated system are not equal, right? They are not equal. Closed system has to do with energy, no energy transfer. And isolated system is just nothing at all, right? So no interaction. And this includes energy, right? So an isolated system is closed, but the closed system is not isolated. And one example that someone once taught me in the past, I think it was one of my lecturers in the past, but basically the best way to explain it is a coffee flask, right? So if you have a coffee flask, let's just use a cylinder. And the coffee flask is not covered, so the cover is opened, right? In this case, right, there can be, okay, no, never mind, let's change that. let's say it is covered, right? Okay, so in this case, now, no, what is it called? No coffee can leave that flask, right? And let's assume it is a good flask, right? So there's no coffee that can leave that flask, and heat cannot leave that flask, right? Because the point of a flask is to store heat. So if it is a good flask, then it means the heat stays in the flask and the coffee stays in the flask. So there's no interaction with the entire environment. The energy of the flask, or what is inside the flask rather, is constant, and the stuff inside the flask itself, the physical things inside the flask, stay in the flask. So a closed coffee flask, well, let's not use the word closed. A sealed, so you don't confuse it with closed system. A sealed flask is an isolated system, right? Because no interaction can occur, right? I hope that makes some sense, right? Because it is sealed. Okay. However, if it is a closed system, then now there's no energy transfer, but there can still be some interaction, right? So if you think of what is the best type of closed system we can think of? If you think of a collision, for example, a collision, the system for that collision can be a closed system because energy is conserved and there's no transfer of energy, but there's still some form of interaction, right? Okay, I hope this makes a lot of sense, but don't worry, we are going to do questions that can maybe help us with our understanding, right? But yeah, so we've looked at energy, and yeah, this chapter is almost like a teaser because chapter 7 is the real deal, right? It is the real deal, and we're going to look at questions, and then hopefully look at chapter 7 in the next video. Okay, so let's start with the questions. Okay, so this is the first question we're going to be looking at, right? By the way, every question you are going to do in videos I cover are going to be from the textbook, like the Eric Mazur practice book. So every practice question is going to be from that book or from past papers, right? So I'm either going to do textbook questions or from past papers, but nothing from any other textbook or anything else, right? Okay, so let's look at this question. It says, to write an expression for the kinetic energy of an object in terms of momentum, its momentum P, and inertia M, right? So they are saying we should write kinetic energy in terms of momentum, right? Okay, we know fundamentally from what we looked at in the theory that kinetic energy is 1/2 times mv squared, right? But now they want it in terms of momentum and inertia. We already have inertia here. We want momentum to be inside here somewhere, which means we have to get rid of this velocity, right? And we know that momentum is equal to mass times velocity. So velocity is momentum divided by mass, right? So logically, we can just go in here and say, therefore, K is now just going to be 1/2m times P over m squared, which becomes 1/2m times P squared over m squared, which becomes P squared over 2m. So m cancels m squared. So another way we can write kinetic energy is as P squared over 2m. So if we have the momentum, but for some reason we don't have the velocity directly, we can easily just write kinetic energy as this, okay? I hope this makes sense, right? Okay, and this is the kinetic energy of an object. So this is what they asked for. This is our answer. However, if we wanted the kinetic energy of a system, we can just write it as a sigma notation, right? It's going to be, so sum of kinetic energies is going to be sum of potential energies. Sorry, sum of momentum squared divided by 2m, right? And this is important because of the next question. Okay, so this is question A. So I hope this makes sense because with this course, you need to get very comfortable with working with variables and not numbers, right? It is much better to work in variables and then put in numbers later. In some cases, you won't even have any numbers and you work purely with variables. Okay, so that's for question A. And then for question B, it now says, if kinetic energy can be written in terms of momentum, right? If it can be written in terms of momentum, as we've already seen here that it can be, right? It can be written in terms of momentum. So if that is the case, how come kinetic energy can change in an inelastic collision, even though the law of momentum of conservation forces momentum to remain unchanged, right? So I hope you can see what they are asking now. They are saying, right? We already know this, right? K is P squared over 2M. In an inelastic collision, this is going to change. We already saw that, right? But this is not going to change. So how is that possible? And that's the question here. Okay. And I don't know, can you think about like why is this? How is it possible that kinetic energy can change and momentum stays the same? What do you think? Okay, 5 seconds. Think 5, 4, 3, 2. Okay, actually, you can pause the video and just think about it. Like it would be more rewarding if you're able to figure it out, or if you are not able to figure it out, but then you still think about it, right? And the key here is that they said here the kinetic energy of a system, right? A system. And this is very possible, right? And the reason is because we have this squared relationship here, right? So because there's a squared relationship, uh, potential, sorry, I keep saying potential because of the P. So because of that square relationship, momentum can change. So the momentum can stay the same while kinetic energy changes, right? Because we are looking at the momentum of a system and the kinetic energy of a system. So let's just take a system, for example. Let's say we have, so I'll just do an illustration. So we have a system of, I don't know if I should do a general proof. Oh, okay. So they don't ask for a proof. They just ask you to explain. So I'll just give you like a scenario. So let's say we have 3 objects in this system. We have object A, object B, object C, right? 3 objects. Okay. So before the collision, so somehow 3 objects collide with each other, which is a crazy scenario. But anyways, initially, what do we have? P1, sorry, PA1I plus PBI plus PCI, right? Is equal to, so let's say PAI is, let's just give it a number. Let's say it is 5, and then PBI is maybe 7, and then PCI is 6, right? And if we add this together, it gives what? 7 plus 6 is 13, plus 5 is 18. So this is 18 kilogram meters per second, right? So this is our initial momentum, right? Yeah. So sum of momentum. Okay. And based on this, we can find our kinetic energy, right? Because it's just going to be the sum of all kinetic energies that we have. Okay. So let's just, for simplicity, let us assume that M is equal to 1 for all of them, right? So our kinetic energy becomes what? 5 squared over 2 plus 7 squared over 2 plus 6 squared over 2. And what does that give? I'm not ready to use my brain for this one, so I'm using my calculator. So over 2 plus 2 plus, and this gives 55 joules, right? So this is initially, and then an inelastic collision occurs. Okay, which means now your kinetic energy changes. We expect that to happen, but now we know, right, that based on the law of conservation of momentum, sum of momentum initial is supposed to be equal to sum of momentum final. So what that means is our sum of momentum is going to stay at that 18 kilogram meters per second. It's going to stay. It is not going to change. However, each momentum can change as long as the sum stays at 18, right? So for example, maybe the 5 goes down now to 3 and the 7 goes up to 8 and the 6 goes up to 7, right? We can see that 8 plus 3 is 11. So this is still 18, right? This is still 18 kilogram meters per second. However, the way the momentum is distributed has changed, right? Now, because of that square, we're now going to have this. Our kinetic energy is now going to be 3 squared over 2 plus 8 squared over 2 plus 7 squared over 2, which gives what? Let's do that quickly. 9 plus... And I get what? 61 joules, right? So what can we see here? We can see that after this collision, the momentum stays the same, but the kinetic energy changes, right? And that is because of the squared. If there was no squared and it was just plus, 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 then nothing is going to change, right? So I hope you can see that. And also, if it was a single object and not a system of objects, then kinetic energy cannot change, right? So, uh, so for a singular object, kinetic energy, sorry, momentum must change for kinetic energy to change. I'll just say note. Okay, so now this is not what the question asked, right? So this is just for your information. What the question asked is for a system, right? So the question wants you to explain why, or rather, how can kinetic energy change when momentum stays the same? And we've already looked at that, right? So it is basically because of that square relationship, right? Because let's just come up with something. Okay, so you don't have to write it exactly how I write it, but the way I would write it is in a system, or let's say after an inelastic collision, momentum stays constant, right? Momentum of the system is constant. However, momentum of each component, right, of the system can change, right? That is possible. So the total momentum is constant. However, the momentum of each component of the system can change, right? And then this can cause a change in systems kinetic energy because of the square relationship. Okay, so this is how I would explain it. And if I was writing a test, I would go into more detail than this, right? So this is just to give you an idea. If you are answering this question, write it in a way that makes sense to you and in a way that you think if someone reads it, they will understand. And in a way that you think covers everything, because in a test, for example, there are going to be 3 marks. You have to say enough to get those 3 marks. Sometimes you're only going to get 2 if you don't say enough. So for example, this is probably only going to get 2 marks. But again, this is just to show you what is going on. And this, when you're doing a test, or even when you're practicing, you don't need to write this, right? This is just for this is just a scenario for illustrative purposes. Okay. Okay, so I hope this question has been useful, right? It is absolutely important that you understand how in a system the fundamental quantity does not change, but it is possible for the way it is distributed to change. So yeah, that is it for that question. We can look at question 5. Okay. So it says 2 objects which have the same velocity, right? But one of them has twice the inertia of the other one. What is the ratio of their momentums and what is the ratio of their kinetic energies? And without writing, you should be able to see that the ratio should just be 2:1, right? Because if you think about it, momentum is mv, kinetic energy is 1/2 mv squared. The point here is we're just multiplying m. We are not doing anything to the m. So the relationship should stay the same. But let's look at it. So we have object 1, object 2. Same velocity, but object 1 has m, but that's twice the inertia of the other one. So if this has 2m, then this has m, right? So that means the ratio of their momentum, this momentum is going to be 2mv, but this momentum is going to be mv. And this kinetic energy is going to be 1/2 times 2mv squared. And this kinetic energy is going to be 1/2 times mv squared. Okay. So logically, we can see that the ratio is just 2:1, right? So if we say P1 over P2, it's just going to be 2mv over mv, which is 2/1, right? K1 over K2 is 1/2 times 2mv squared divided by 1/2 mv squared. V squared cancels V squared, m cancels m, 1/2 cancels 1/2. And just like before, it left it 2/1. So what these last 2 questions have done is they've shown you how similar momentum and kinetic energy are. They are 2 different things, but they are similar because they both depend on speed and mass, right? Or speed and inertia, rather. Okay. The only difference is with momentum, for example, it has a direction, right? But with kinetic energy, you square the velocity, so it has only a magnitude. But they both kind of have the same sort of physical meaning. If you have a lot of momentum, then you also have a lot of kinetic energy, right? Okay, but yeah, this question was fairly straightforward. We can now look at this one, which is actually the, let's call it the main event of this chapter. Okay, so before we look at this question, I want you to just recall or revise is that the total energy of a system is given by what? Kinetic energy plus internal energy, right? And in a closed system, this is conserved, which means there's no change. the initial energy is equal to the final energy, right? So what that means is delta E is 0, right? So delta K plus delta E internal should be 0, right? Because delta E is 0, okay? So that means we can say delta K is equal to negative delta E internal. Okay, and the reason I'm explaining this is so we understand that a change in kinetic energy would correspond to a change in internal energy. So just store that somewhere in the back of your mind, because we're now going to look at this question. It is a loaded question, okay? So let's start. A 52 kilogram ice skater, okay? This value includes a body, a clothing, and several 1 kilogram snowballs she's carrying. So that 52 kilogram accounts for everything that she's carrying, right? So she's at rest on ice. Okay, that's the full stop there. Yeah, first block of information. Then she throws a snowball to the right at 10 meters per second. Okay, bam. What is a speed after the throw? Is a velocity to the left or to the right? Okay, so let's see what we have. So initially, we have this 52 kilogram ice skater. So initial, and also it is helpful to just do a sketch or a drawing of the scenario before you try it, right? So we have the skater. Boom. I'll just draw a stick figure. Yeah. And she's carrying a bunch of snowballs. She's carrying a bunch of snowballs as such. Okay. And the total weight, okay, she's skating. So let's give her nice skating shoes. Okay, perfect. And her total weight is 52 kilogram, and she's at rest, which means her velocity is 0 meters per second, right? So this is the initial case. And then she's at rest on ice, okay, which means negligible friction. And then she throws a snowball to the right at 10 meters per second. Okay, so you know what? Let's assume the snowballs are in a backpack because she's carrying them, so there's no way she can throw them because her hands are not free. So let's change our drawing. Okay, so there's a backpack with snowballs inside. Okay, so then in the final case, the second case, okay, what does she do? She now throws the snowball to the right, okay? Snowball goes this way at 10 meters per second. And what are we told? We are told that the snowballs are 1 kilogram, right? So 1 kilogram in mass. Okay, and she throws it. Okay, she has a nice backpack. So this is after throwing it. Okay, anyways, she throws this thing, and then we now know, okay, so logically we know that after this throw, our weight should now be 51 kilograms, right? Because now it is without that 1 kilograms, okay? Okay, so she throws it. Now, what do we want to know? We want to know a speed after the throw, right? And we also want to know is a velocity to the left or to the right. So now we can just use conservation of momentum, right? because this is basically a, I don't want to say collision, but like it is an interaction between two objects, right? So we can now say sum of momentum before is equal to sum of momentum final, right? What is the initial momentum? It is 0, right? 52 times 0 is equal to that ball 1 times 10, okay, plus 51 times V, I'll call it G, VGF. G is the girl, right? And this is the ball. So VB and VG is unknown, okay? So this is what we have. So actually you should not be like me, rather put in your variables first. So initial, it is going to be mg plus mb times v initial equals to mb times vb final plus mg times vg final, right? So now that we know all of this, we can solve for vg final. This is 0, so vg final is going to be minus 10 over 51 which gives me an answer of minus 0.1961 meters per second. So for the ball to go 10 meters to that side, she goes 0.196 in the opposite direction, right? So we can see that a speed is equal to 0.1961 meters per second because they asked for speed, which is a scalar, okay? And then they also asked, is a velocity to the left or the right? And the answer is she throws the ball to the right, so a velocity has to be to the left because it is in the opposite, right? If she throw the ball to the left, then a velocity would be to the right. If she threw the ball north, a velocity will be south. If she threw the ball east, a velocity will be west, just opposite, right? But now that's just A. Then now B now says calculate the coefficient of restitution for this event. Okay. And if you remember, we have that formula for coefficient of restitution, right? So E is equal to negative V2 final. In this case, we can treat 2 as our girl, right? So VG final minus VB final divided by VG initial minus VB initial. So what have I done? I've just replaced 2 with G and 1 with B. You could have done it the other way around. It doesn't matter as long as it is consistent at the top and at the bottom, right? Okay, so now looking at this, what do you think? Like, based on what you've seen here, what do you think the what is it called? Coefficient of restitution should be just without calculating, just by looking at it. Initially they are traced, and then they have a collision, and then now they have velocities. Okay, so let's calculate it. Okay, wait. Coefficient of restitution for this event. There seems to be a problem in this scenario, but we're going to look at it now. Okay, so if we just substitute in the values, we're going to see there's a problem here because we have minus, and our VF is what? Our VGF is minus 0.1961, okay, minus our VBF, which is 10, right? Divided by, and this is where the problem comes in because now what do we have? We now have 0 because they are both at rest at the start. So we now have 0 minus 0, which is basically impossible, right? So we have 0 minus 0. So what do you think? And I'm pretty sure you've done something like this in maths, and it basically, we find the limits as the denominator goes to 0, and the limit, as I'll just call it denominator of E, is going to be infinity, right? So what you actually see is that our coefficient of restitution is infinity simply because it starts from rest. And it is always going to be like this if it starts from rest, because your bottom is going to be 0, right? So what we can see is that this, and this is something you should have been able to see from the start. Well, you didn't have to say that it was infinity, but you'd have been able to see that it is greater than 1, because this is an explosive interaction, right? Explosive meaning they are separating from each other, okay? Okay, so that is for question B. So it was a problem, but it is correct. It is just, this is the theory sort of breaks down when it starts from rest. That doesn't mean there's infinite energy or anything like that. Okay, now we can look at C. So before we look at C, they give us some additional context. The context is now that she now throws a second snowball, but this time at a speed of 20 meters per second to the left. Okay, so this was what happened first. So she did this, she was moving at VG. Okay, so this final of the first question is now going to be our initial scenario, right? So she was already moving, okay? And now we already know what VG is, right? We know it is 0.1961 to the left. Just going this way, okay? So let's forget about this first ball. We don't need it anymore. So now she was moving this way, okay, at this velocity. And then she decided to throw a ball again, okay? She decided to throw a ball, but this time she threw the ball to the left, right? So, yeah, so she's 51 kgs. So she threw a second ball, which means she's now going to be what? She's now going to be 50 kgs, right? Okay, so I just flipped the image because I wasn't going to try it again. So now this is 1 kilogram and it is thrown at 20 meters per second. Okay. And her weight now drops again to 50 kilograms because now she has lost 2 kgs, right? And now we don't know again what the final velocity is. Okay, I hope this is making sense, right? So it is just a sequential thing. There was one sequence and then now it is continuing onwards, right? So we want again a speed after the throw is a velocity to the left, to the right. And then we do the exact same thing again, momentum, right? Sum of momentum initial is equal to sum of momentum final. And make sure you understand that the initial conditions for question C is equivalent to the final for question A, right? Okay. So now we're going to have 50 times, 51 times the speed of 0.1961 is equal to a 1 kilogram. Sorry, our sign convention, we've been using right as positive. I didn't explicitly state it actually, but right is positive because we took 10 to be positive. So that means actually this is supposed to be negative, then it is 51. And then this is equal to 1 kilogram times negative 20 plus 50 kilogram times VGF, right? Okay. So now she's no longer starting from rest. So there is an initial momentum, right? So VGF, if we rearrange, is going to be 51 times 0. Sorry. Yeah, 51 times minus 0.1961 plus 1 times 20. So that negative 20 becomes a plus divided by 50, right? And if we solve for this VGF, let's see what does it become. Okay, and I get 0.199978 meters per second, which is basically 2 meters, sorry, 0.2 meters per second, right? So this is a new velocity and a speed. Okay, speed is the same exact thing. So I'm just putting absolute value to specify that it is speed, right? And it is going to be to the right because we got it as a positive value, right? Okay, so we can see now she was moving to the left, then she's basically using the snowballs to move around, right? Because actually this lady or this skater is stuck in a nightmare because there's no friction. And if you think about it, if there was no friction, life would not exist. We would all die basically because now in our world there's no friction. So she keeps on going and going and going forever. That speed stays constant forever. So she can't stop, right? So she needs to use snowballs to change her direction. Okay, so that's what we can see. Then D now says calculate the coefficient of restitution for this event. Okay, now there's an initial velocity, right? Now there's an initial velocity, which means that it is not going to give us infinity like it did before, right? So E is going to be negative Vg final minus Vb final divided by Vg initial minus Vb initial, okay? So now, oh, actually, it does still give us infinity. Okay, I'm going to explain why now. But now we're going to have negative 0.2 minus 20 divided by, now they have an initial velocity, but they are moving together, right? So this is where relative velocity becomes important because this term represents relative velocity. So even though they both have velocity, they both have the same velocity of, so they should have been minus 20, so plus 20. They both have the same velocity of 0.1961, right? So what happens is actually relative to each other, they are at rest. So it becomes minus 20.2 over 0 again. And just like before, we just find the limit, right? And by finding the limits, it just goes to infinity, right? Like before, okay? So again, it is explosive as well, right? So if you remember when we're going over the theory, I said something about explosive interactions, right? I said for an explosive separation, there's energy going into the system, right? Because something cannot be at rest and then randomly just gain speed. There had to be some energy injected into it, right? So somehow there's some energy entering this system to allow allow the coefficient of restitution to be above 1. Okay, and we're going to get to it because now question E says calculate the change in kinetic energy in this second event. Okay, change in kinetic energy of this second event. So we're just going to say delta K is going to be K final minus K initial, right? So delta K is going to be 1/2. And now find the final kinetic energy of each of these guys. So 1/2 m girl v girl squared, okay, final, plus 1/2 m ball v ball final squared, minus 1/2 m girl v girl initial squared, minus 1/2 m ball v ball initial squared. So a change in kinetic energy becomes 1/2, and the girl has a weight of 50 times our velocity, which we got to be 0.2 squared. And for kinetic energy, we don't need to worry about the signs, right? So plus 1/2 times the ball, 1 kilogram times 20 squared, minus 1/2 times the girl, again 50 times the initial velocity of 0.1961 squared. Again, we don't care about the signs. Minus 1/2 times 1 times 0.1961 squared, right? So actually, because they were together in the initial state, you could have done this together as one. So you could have written it as 1/2 times 51, 0.1961 squared, which should give you the same answer. Actually, that would save us time. So I'll just treat it as one object, but it doesn't matter as long as you account for the speed correctly, right? So our delta K now becomes, going to whip up my calculator. Yeah, and I get a delta K of 200 joules, which is like quite a good chunk of energy, right? Okay, so what you see is that the kinetic energy increased, which sounds like magic, doesn't it? Because usually energy is usually lost. Yeah, it is very difficult for you to get a system where the energy stays constant. But in this case, energy increased, which is why they've now asked us, where does this added energy come from? We know there's energy, but where does it come from? And that brings me back to when we started this question, and I said we need to understand energy is kinetic plus internal, right? So for that kinetic to go up, internal must have gone down, right? So the kinetic energy increased by 200, which means internal energy must have decreased by 200. And where is internal energy from? It can be the chemical energy. It is, in this case, it is the energy that our muscles transfer, right? So our body provides the energy that she needs. For you to walk, you are burning energy, right? And as we see in question F, it is calories. It's called calories. If you like to gym or work out, because I do, you should be familiar with the term calories, right? It's just another measure of energy. So where does the extra energy come from? It comes from internal energy, right? From a broad sense. Yeah. So depending on the marker, you should get the mark for just saying this. However, you can specify that the internal energy is just chemical energy produced by the body, right? Because when you eat food, you are converting energy. right? So this was an explosive scenario that we looked at, and we can see that energy needed to be injected or transferred into the system. Okay. So that's it for E. And then last question for F, which is the last question for this chapter, at least for now, is they say 1 food calorie is equal to 4184 joules. How many food calories does she burn by throwing the second snowball? And we can easily do that. So we can just say calories over 200 is equal to 1 over 41. It's 41 what? 4184, right? So 1 calorie is 4184. We want to see how many calories is 200. So number of calories becomes 200 divided by 4184, which becomes 0.0478 calories, right? So you can see how minuscule that is. It isn't even up to half a calorie. So yeah, that is why like if you have ever run on a treadmill, you know, like it counts the amount of calories you burn, and like you could have been running for 10 minutes, but it says you've only burned 6 calories. So yeah, you do need to release a lot of energy to burn a significant amount of calories, right? Okay, so I hope that this makes sense, right? I hope it really makes sense. And I hope this question makes sense because it helps a lot. But this is not where this chapter ends because, like I said, this chapter is just part 1 of energy because in chapter 7, we're going to continue with energy. So I'll just advise you that after watching this video, you go on to watch the video for chapter 7, right? Because, and look at the questions there as well. Okay, but that's it for this chapter, and I'll see you in the next video. Like and subscribe. I'm joking. Okay, bye bye.